So this is going back to the 3.2 notes. So if you recall, we didn't do that last page of the 3.2 notes, and that's because I like to do the addition rule before I go over this. The book has this first, but I find that learning the addition rule is a little bit helpful when you discuss this. So basically, we've learned in section 3.2 that the probability of finding the probability of A and B is equal to the probability of A times the probability of B given A. And if you take this equation and you divide both sides by the probability of A, the probability of A over here gets eliminated. So really, the probability of B given A, which is what's on the right side now, is equal to the probability of A and B divided by the probability of A. And I want you to notice that you're dividing by what you are given. So divide by the given. So this is helpful if you want to figure out a conditional probability. So sometimes you don't want to find out what the probability of just a single event is, but you want to find out what is the probability of an event given that you've already had another event happening. So let's find the probability of an airplane flight departs on time, or the probability of an airplane flight departs on time is 0.89, probability that a flight arrives on time is 0.87, and the probability that a flight departs and arrives on time is 0.83. So we want to find the probability that a flight departed on time. So let's say you're standing in the airport and well, let's say you're on the plane. Let's say you're on a plane, and we want to find the probability we're going to get to our destination on time. So we want to find the probability that I guess no. We're standing in the airport, and let's say we're trying to figure out what time the plane is going to depart, but we know that the plane arrived on time, right? We know that the plane arrived on time. And if we know the plane arrived on time, we use our formula, right? So we always, on the numerator, we always take the probability of D and A, and we always divide by what we're given. Well, we're given that it arrived on time. Well, the probability that both happened is 0.83, divided by the probability that it arrives on time is 0.87. And that is 0.9540. Okay, now let's do the reverse. Find the probability that a flight arrives on time given that it departs on time. So this is probably the one that we care a little bit more about, right? So if we know a plane departed on time, what's the probability that our plane is going to be here on time? So the probability that it arrives on time and departs on time divided by probability it departs on time. So again, that's 0.83. That's the probability of A and D is the same thing as D and A. But instead of dividing by A, we're dividing by D because we're given D now. And we're given the probability that it departs on time is 0.89. So this is 0.9326. Notice that these are not the same. Conditional probabilities are not reversible. Okay, they are asking different questions. And so that is an important thing to realize. Now that we've talked about and used the formula a little bit, let's talk about something a little bit more complicated. So when you actually want to know a conditional probability, it might be something in a situation like this. So we have a virus that infects 1 in every 200 people, and a test is used to detect the virus in a person is positive 80% of the time. And if the person has the virus, or that's if the person has the virus, and 5% of the time if the person does not have the virus. And this is called a false positive. So when you are taking a medical test, sometimes medical tests can get the test wrong, and sometimes the medical test might say, well, with a 5% likelihood you might get this false positive. So in other words, the test says you have a virus, but in fact you actually don't have a virus. So let's draw a tree diagram for this. So we're going to make a tree diagram of infected individuals and I prime for not infected individuals. And how many people are infected? Well, 1 in every 200 are infected, which is, as a decimal, I'm going to do decimal 0.005. And let's fill out the entire tree diagram here. So that means the people that are not infected, it's 0.995. And this is why tree diagrams are so useful, because you can put the events at the ends of the arrows, and then the branches should always sum to 1. All right, so the next one is a virus. So is about a virus. So and if the test actually detects the infection. So if the person is infected, they take this test, and it's either going to be a positive or it's going to be, I'll use an N for negative, positive, or it's going to be negative. Now, if they're infected, it says it's positive 80% of the time, which means that 20% of the time the test does not detect the virus, okay? And then if they're not infected, there's actually a 5% chance that the test says you have the virus when in fact you don't, which is 0.95. So this is basically the setup for the problem. People are infected, they're not infected. If they're infected, there's an 80% chance the test says they're positive, 20% negative. And if they're not infected, there's a 5% chance they're positive and a 95% chance it's actually negative. So the question here is, if a person tests positive, in other words, we're given that the person tests positive. So we want to find the probability. If a person tests positive, determine the probability that the person is infected. So we want to find the probability of infection given a person tests positive. And this is really what we want to know, right? We want to know that if I take this test and I get a positive result, what's the probability that I actually do have the virus? And it's not 80%. 80% is the reverse of that. 80% is the probability of testing positive if I have the virus. But I don't know if I have the virus. That's the whole point of the test. So what we're going to do is we're going to use our conditional probability formula. We're going to use the probability of I and P, and we're going to divide by the probability of, and we always divide by what we're given. What's the probability of testing positive? Okay. So I'll use a different color for this. So the probability of getting infected and a positive result, well, there's two ways this can occur. It can be infected and positive. Actually, there's only one way. Infected and positive. It's this branch right here. And I told you in section 3.2 that when we make a tree diagram like this and I want to find the probability of and, we multiply along the branches. So that's 0.005 times 0.8. Now, the probability of getting a positive result, there's actually two ways. I can be infected and get a positive result, or, and this is why I like to talk about the addition rule first, or I can be not infected and get a positive result. Well, the probability of getting infected and a positive result is exactly what the numerator is. But we remember from section 3.3, what we just talked about in the previous section, that we are going to add 0.995 plus 0.05. And so this is the probability of getting a positive result, because this is getting a positive result if I'm infected, and this is getting a positive result if I'm not infected. Okay? And the answer to this is 0.0744, or about 7.4%. So think about this. If this test says I have a positive result, there's a 7.4% chance that I am infected with the virus. So is this a good test? Not really. And this is why it's so important, if a disease is rare, to have a very accurate test, because this test isn't really that accurate. I mean, if you go back to the tree diagram, there's a 20% chance of getting it wrong, right, if I have the virus. That's not good at all. And 5% is still a pretty high false positive rate, in my opinion, too. And so what happens is you have so few people that actually have the virus that the test actually is getting it wrong so much, because you have such a high false negative rate. right? Only 80% is positive. It's positive when you even do have the virus, and that's a problem. And you might say 80% is not that bad. 80%, like that's a B minus, right? But a B minus in terms of a test, especially when you have a rare test, actually results in a very, very poor test. So try to answer this question on your own. So I would pause the video here and try to answer the last question on your own here. So it says if a person tests negative, so that's what we're given. We're given the negative result. Determine the probability that the person is not infected. So in our numerator, we have not infected and negative. In our denominator, we have the probability of negative. So not infected, that's 0.995 times the negative results, which is 0.95. And we want to divide by the probability of getting a negative result, which is going to be 0.995 times 0.95, plus we have to add the probability of getting a negative result if we are infected. So that's 0.005 times 0.2. And this is going to be nearly 100% because, and it is. You should get 0.9989. Okay, so hopefully you got that for your answer. There's actually going to be a separate worksheet assigned that goes over this. So make sure that you look at that worksheet, download it, do it on a separate sheet of paper, and then I'll have a separate video going over that worksheet just to make sure you understand the concepts. But I highly advise you practice that worksheet. You're not turning it in or anything. You just make sure you look over those problems and practice those, especially for these types of tree diagram problems, because on your test, there is going to be a problem that is related to a tree diagram like this. Okay,